Look up at the night sky, really look at it. Those countless pinpricks of light aren't just random specks. They're clues to a puzzle so vast, it's taken humanity centuries just to scratch the surface. Every star, every galaxy, every flicker of distant energy holds secrets that rewrite the rules of reality itself. And today, we're diving headfirst into the greatest enigmas of all the 32 mysteries of the universe's blueprint, a deep dive into celestial architecture. This isn't just a tour of the cosmos, it's a backstage pass to the hidden blueprints that shape everything from the tiniest atom to the sprawling web of galaxies. Think about this for a moment. The universe isn't chaos. It's a finely tuned machine operating on laws so precise that even the slightest change would unravel existence as we know it. Dark matter, an invisible force binding galaxies together, makes up most of the universe, yet we've never seen it. Black holes, those cosmic vacuum cleaners, warp time and space so drastically that they twist the very fabric of reality. And then there's the question of why the universe even exists at all. These aren't just scientific curiosities, they're the threads of a grand tapestry, woven with precision beyond our wildest imagination. But here's the most thrilling part. We're on the verge of breakthroughs that could crack these mysteries wide open. New telescopes peer deeper into space than ever before. Quantum physics challenges our understanding of reality, and every discovery brings us closer to seeing the universe not as a cold, empty void, but as a living, breathing masterpiece. So if you've ever stared up at the stars and felt that tug of wonder, that hunger to understand what's really out there, you're in the right place. This journey isn't just about facts, it's about seeing the cosmos with new eyes. Ready to unravel the universe's best-kept secrets? Let's begin. The first mystery on our cosmic journey is perhaps the most baffling of all: dark matter. Picture a spider's web, invisible to the naked eye, yet strong enough to catch prey mid-flight. That's dark matter, an unseen force weaving through the cosmos, holding galaxies together like cosmic glue. Without it, stars would fling apart, and the universe as we know it would unravel. Yet despite making up roughly 27% of everything in existence, dark matter refuses to show itself. It doesn't emit light, absorb it, or interact with ordinary matter in any way we can detect. So how do we even know it's there? The answer lies in the universe's own architecture. When astronomers measure the speed of stars orbiting the center of galaxies, they find something strange. Those stars are moving far too fast to be held by the gravity of visible matter alone. It's as if an invisible hand is gripping them, keeping them in place. This missing mass, this ghostly anchor, is dark matter. But what is it? Some theories suggest it could be made of undiscovered particles, ones that barely interact with the world we know. Others propose even wilder ideas, like tiny primordial black holes forged in the chaos of the Big Bang, or even particles from hidden dimensions bleeding into our own. The hunt for dark matter is one of science's greatest detective stories. Deep underground, in labs shielded from cosmic noise, detectors wait for the faintest whisper of a dark matter particle passing through. In space, telescopes map the distortions of light caused by dark matter's gravitational grip, tracing its shadowy fingerprints across the sky. And with every experiment, every observation, we get closer to cracking the code. Because dark matter isn't just a cosmic curiosity, it's the hidden framework of reality itself, the scaffolding upon which galaxies and perhaps even life are built. Without it, the universe might be a very different place or might not exist at all. So the next time you look up at the night sky, remember, what you see is just the surface. The true structure of the cosmos is written in something far more elusive, something we're only beginning to understand. And that brings us to our next mystery, one that bends not just space but time itself. If dark matter is the invisible glue holding galaxies together, then dark energy is the universe's silent rebel pushing everything apart at an ever-increasing speed. Imagine blowing up a balloon, but instead of slowing down as it expands, it inflates faster and faster, defying all logic. That's exactly what's happening to our cosmos. The universe isn't just growing, it's accelerating, stretching space itself like an unstoppable force. And the culprit behind this cosmic speed up, a phantom we call dark energy. Here's what makes this mystery so perplexing. Back in the 1990s, astronomers studying distant supernova made a jaw-dropping discovery. These exploding stars, billions of light years away, were dimmer than they should have been, meaning the space between us and them had stretched more than anyone predicted. The universe wasn't just expanding, it was doing so faster and faster, as if some unseen energy were pressing down on the cosmic gas pedal. Even Einstein, who once proposed a similar concept only to dismiss it as his greatest blunder, might be stunned to see his ideas resurrected in such a bizarre way. So what is dark energy? The leading theory suggests it's a property of space itself, a kind of background hum of energy woven into the fabric of reality. Think of empty space not as true nothingness, but as a seething foam of particles popping in and out of existence, generating a repulsive force that drives galaxies apart. But here's the twist: if this energy exists, it should be unimaginably weak, yet somehow it's overpowering gravity, the force that shaped the cosmos for billions of years. Alternative theories are even wilder. Some propose entirely new laws of physics, while others suggest dark energy could be the signature of hidden dimensions or even a cosmic field left over from the Big Bang. The implications are staggering. If dark energy keeps accelerating the universe's expansion, distant galaxies will eventually vanish beyond an unreachable horizon, leaving future civilizations with a night sky nearly empty of stars. The cosmos could end not with a bang, but with a whisper, a cold, lonely fade into darkness. Yet every unanswered question is a chance for discovery. Telescopes like the James Webb Space Telescope are mapping the universe's expansion in unprecedented detail, while experiments on Earth probe the fundamental nature of space and time. Dark energy isn't just a puzzle, it's a key to understanding the universe's destiny. And as we peel back its layers, we're forced to confront an even deeper mystery, the very fabric of reality itself. What if space isn't the static stage we imagine, but something far more dynamic? Something that bends, twists, and maybe even remembers. Einstein changed everything we thought we knew about space and time. But what if even his revolutionary ideas were just the tip of the iceberg? Picture spacetime not as a rigid stage where cosmic events play out, but as a dynamic, twisting fabric that bends under the weight of stars and ripples with the echoes of colliding black holes. This is the mind-bending reality of our third mystery, the true nature of spacetime itself. Take gravity, for example. Newton saw it as a simple force pulling objects together, but Einstein revealed it something far stranger, the warping of spacetime itself. Imagine placing a bowling ball on a trampoline. The heavier the object, the deeper the dent it creates, and the more nearby objects spiral toward it. That's gravity in action, not a force but the curvature of the cosmic fabric. When two black holes collide, they don't just create a splash. They send shockwaves through spacetime itself, distortions we can now detect as gravitational waves. These ripples, first observed in 2015, proved spacetime isn't static. It's alive, responsive, almost breathing. But here's where things get even weirder. While relativity paints spacetime as smooth and continuous, quantum mechanics suggests the opposite, that at the tiniest scales, spacetime might be pixelated, like a cosmic digital image. Think of sand on a beach. From afar, it looks like a seamless surface, but up close you see the grains. Some theories propose spacetime is built from indivisible quanta, tiny packets of reality so small, 1,000,000 billion of them could fit across a single atom. If true, this means there's a fundamental limit to how finely we can slice the universe, a smallest possible piece of space and time. The problem: these two visions of spacetime, Einstein's smooth fabric versus quantum mechanics' grainy pixels, refuse to fit together. It's like trying to merge a painting and a mosaic into a single image. This clash isn't just academic, it's a roadblock in our quest to understand the universe's deepest laws. Black holes, where both gravity and quantum effects reign supreme, become impossible to describe without a unified theory. Some physicists speculate that spacetime might emerge from something even more fundamental, like information or entangled quantum particles. Others wonder if what we call space is just a holographic projection of a deeper, stranger reality. Every unanswered question is a crack in our understanding, but also an invitation. Experiments with ultra-precise atomic clocks measure whether time flows differently at microscopic scales. Particle colliders hunt for signs of spacetime's granularity. Even our GPS satellites, which adjust for spacetime's curvature, are unwitting tools in this grand investigation. Because spacetime isn't just the backdrop of the universe, it's the protagonist, shaping everything from the fate of galaxies to the ticking of your wristwatch. And as we peel back its layers, we're forced to ask, if spacetime isn't what we thought, what else might we have wrong? That uncertainty leads us to the next enigma, one where the universe's rules seem to rewrite themselves entirely. What if everything you know, every choice you've made, every law of physics governing your existence is just one possibility among countless others? This isn't science fiction. It's the multiverse hypothesis, a staggering idea that our universe might be a single bubble in an endless cosmic froth. Imagine a library where every book contains a different version of reality, each with its own rules, its own history, even its own you. Somewhere, dinosaurs never went extinct. Elsewhere, gravity is twice as strong, or the speed of light is slower. And if theories like string theory or quantum fluctuations are correct, these parallel worlds might not just be possible, they could be inevitable. Let's break this down. Start with the infant universe, a seething cauldron of energy in the moments after the Big Bang. Quantum fluctuations, tiny, random ripples in the fabric of reality, could have caused space to expand at different rates in different regions. Picture blowing soap bubbles. Each one inflates independently, becoming its own isolated universe with its own unique physics. Our cosmos, with its perfect balance of forces allowing for stars, planets, and life, might simply be one lucky bubble among infinite others where the conditions were less hospitable. Then there's string theory, which suggests the fundamental building blocks of reality aren't particles but vibrating strings. These strings could vibrate in different ways, creating alternate universes with entirely different laws. Think of a cosmic piano where each key plays a different set of physical constants, some harmonious, others chaotic. But here's the catch: if these other universes exist, they're forever beyond our reach, separated by stretches of space expanding faster than light can cross. The implications are dizzying. If the multiverse is real, our universe's fine-tuned laws, like the precise strength of gravity or the mass of an electron, aren't miraculous. They're just one random outcome in an infinite lottery. There could be universes where atoms never formed, where time runs backward, or where black holes evaporate in seconds. And yes, somewhere out there, another version of you might be living a life shaped by entirely different choices. But how could we ever prove something so extraordinary? Some scientists hunt for cosmic fingerprints, anomalies in the cosmic microwave background, the afterglow of the Big Bang that might reveal collisions with other universes. Others simulate multiverse scenarios in quantum computers, testing whether alternate realities could emerge from mathematical inevitability. Skeptics argue it's untestable, more philosophy than science. Yet the very possibility forces us to confront a humbling thought. Our universe might not be the grand, singular masterpiece we imagined, but one stroke in a canvas without edges. And that uncertainty leads us to the next mystery, one that challenges not just where we are, but when we are. Is time real, or just an illusion woven into our perception? If the multiverse stretches our imagination across space, quantum entanglement shatters our understanding of connection itself. Picture two coins flipped simultaneously on opposite sides of the galaxy, yet somehow they always land matching heads or tails. This isn't magic, it's quantum entanglement, a phenomenon so bizarre that Einstein himself dismissed it as spooky action at a distance. Yet decades of experiments confirm it's real. Particles born from the same quantum event remain mysteriously linked, instantly mirroring each other's states no matter how far apart they drift. Here's what makes this so revolutionary. In our everyday world, influence travels at the speed of light. A text message takes time to reach its destination. A shout across a room arrives moments after it leaves your lips. But entangled particles defy this logic. Change the spin of one electron here on Earth, and its paired sibling halfway across the cosmos knows instantly, as if space and time don't exist for them. It's not a signal or a wave, it's a fundamental connection written into the fabric of reality itself. Physicists are still unraveling how this works. One radical idea suggests entanglement might be evidence of hidden dimensions, invisible threads stitching the universe together behind the scenes. Imagine ants crawling on a sheet of paper, unaware that their flat world is just one layer of a vast, folded origami. Could entangled particles be sensing these deeper folds? Others propose an even wilder theory, that the universe operates like a hologram, where what we perceive as 3D reality is actually a 2D projection encoded at the cosmic horizon. In this view, entanglement isn't spooky. It's just the universe remembering that seemingly separate particles are still part of the same underlying code. The implications are staggering. If entanglement holds, it could rewrite our understanding of space, time, and even the nature of information. Some scientists speculate that black holes might use quantum entanglement to preserve data swallowed by their event horizons, like cosmic hard drives storing secrets in their gravitational grip. Others wonder if the entire universe was once a single, infinitely entangled state. A cosmic egg where every particle knew every other, and the Big Bang was the moment that web began to unravel. Yet for all its mystery, entanglement isn't just theoretical. It's the engine behind emerging technologies like quantum computing, where linked particles perform calculations at speeds impossible for ordinary computers. Satellite experiments have successfully entangled photons over thousands of kilometers, paving the way for unhackable quantum communication networks. Even nature might exploit this phenomenon. Some researchers suspect photosynthesis relies on quantum tricks to funnel energy through plants with near-perfect efficiency. So while Einstein may have been unsettled by entanglement's defiance of classical physics, today it's a beacon guiding us toward deeper truths. It whispers that the universe is far more interconnected than we ever dreamed, not a collection of isolated objects, but a vast, whispering network where every particle remembers its roots. And that realization leads us to the next enigma, the universe's most enigmatic architects, black holes, where the rules of reality don't just bend, they break entirely. Black holes aren't just cosmic vacuum cleaners, they're the universe's ultimate enforcers of silence. Once something crosses their event horizon, it's gone forever, or so we thought. Here's the paradox: quantum mechanics, the rulebook for reality at its smallest scales, insists that information can never be destroyed. Every particle, every interaction, leaves an indelible mark on the universe. Yet black holes, according to Stephen Hawking's groundbreaking work, slowly evaporate over eons, leaving behind nothing but a faint whisper of radiation. So what happens to all the information they swallowed? Does it vanish into oblivion, or is it somehow preserved in a way we can't yet see? This isn't just a technicality, it's a battle for the soul of physics itself. Let's unpack the conflict. Imagine tossing a book into a fire. The pages burn, but the information, the words, the ideas isn't truly lost. In theory, with perfect knowledge of the smoke, the ashes, even the heat radiating outward, you could reconstruct every sentence. Quantum mechanics says the universe works the same way. Information is always conserved, just rearranged. But black holes defy this. Hawking radiation, the energy they emit as they evaporate, appears random, carrying no trace of the stars, planets, or unlucky astronauts that fell in. It's like burning a library and getting back only blank pages. This contradiction has split physicists into warring camps. One side argues that information truly is lost, and quantum mechanics needs rewriting, a heresy to many. Others propose wild solutions, like the idea that black holes don't destroy information but scramble it beyond recognition, like a cosmic blender. Picture a hard drive crushed into a black hole singularity. Its data might still exist, but encoded in the gravitational ripples of the hole's surface, a holographic fingerprint of everything it consumed. There's even a radical theory suggesting black holes might not have interiors at all. What we perceive as a bottomless pit could be a flaw in spacetime itself, a frozen storm where time grinds to a halt at the horizon. The stakes couldn't be higher. If information can escape black holes, it might be through mechanisms we've yet to imagine: wormholes, hidden dimensions, or quantum entanglement threading the needle between the inside and outside. Some researchers speculate that Hawking radiation isn't random after all, but subtly imprinted with the history of what fell in, like a message in a bottle tossed from the edge of oblivion. Experiments with lab-grown, analog black holes using sound waves or light to mimic event horizons are testing these ideas right now. But here's the twist: this paradox isn't just about black holes. It's a mirror held up to the universe's earliest moments. The Big Bang, too, was an information bottleneck, a singularity where the rules we know break down. If we can solve the black hole puzzle, we might glimpse how reality itself emerged from the chaos of creation. Because whether it's a dying star collapsing into darkness or the birth of the cosmos, one truth remains: the universe never forgets. It just keeps its secrets well hidden. And that brings us to the next mystery, one that takes us back to the very beginning, where time, space, and all we know flickered into existence from something even stranger. The Big Bang wasn't an explosion, it was the opening act of reality itself. Picture a single point of infinite density, hotter than a trillion suns, containing all the energy that would ever exist in our universe. Then, in a fraction of a second, space stretched faster than light, matter flickered into being, and time began its relentless march forward. But here's the haunting question: what ignited it? What force or fluke could conjure an entire cosmos from nothingness? One leading theory points to quantum fluctuations, tiny, unpredictable ripples in the fabric of existence. Even in a perfect vacuum, particles blink in and out of reality, borrowing energy from the future to exist momentarily. Could the universe itself be the ultimate quantum fluctuation, a bubble of spacetime that refused to pop? Imagine a cosmic lottery where every possible outcome plays out, and our universe just happened to hit the jackpot, stable enough to expand for billions of years, yet dynamic enough to forge galaxies and life. Then there's the brain world scenario inspired by string theory. Picture our universe as a three-dimensional membrane floating in a higher dimensional space, like a single sheet of paper in a vast, unseen library. If another brain collided with ours, the impact could have unleashed the energy of creation itself. The Big Bang wouldn't be a beginning but a collision, an echo of something grander happening beyond our dimensional reach. But the most bewildering clue lies in the universe's fine-tuning. The precise strength of gravity, the exact mass of electrons, even the density of dark energy. If any of these values were slightly different, stars wouldn't ignite, atoms wouldn't bond, and life as we know it couldn't exist. It's as if the cosmos were engineered for complexity. Some scientists argue this points to a multiverse, where countless universes with random laws exist, and we simply inhabit the one where conditions are just right. Others whisper of something more profound, that consciousness itself might play a role in shaping reality, that the universe is somehow aware of its own existence. Every answer only deepens the mystery. Telescopes probing the cosmic microwave background, the afterglow of the Big Bang, search for imprints of primordial gravitational waves, echoes of inflation's violent expansion. Particle accelerators recreate fractions of the universe's first seconds, hunting for relics of supersymmetry or hidden dimensions. Even the humble neutrino, a ghostly particle that barely interacts with matter, might carry secrets from the instant of creation. The Big Bang's origin isn't just a scientific puzzle, it's a mirror held up to our deepest existential questions. Are we the product of chance or part of something intentional? Is the universe a lone accident or one note in a symphony of realities? And if we ever uncover that first spark, will it bring us closer to understanding or reveal how much wonder still lies beyond our grasp? This fine-tuning leads us to the next enigma, where the universe's delicate balance tips from chaos into order, the mysterious dance of matter and antimatter that should have annihilated us all. The universe doesn't just exist, it permits existence. Think about that for a second. Gravity could have been stronger, ripping stars apart before planets formed. The mass of an electron might have been different, preventing atoms from bonding. Even the density of dark energy, if slightly tweaked, would have either crushed the cosmos into a black hole or scattered matter too thin for galaxies to ignite. Yet here we are, in a universe where every constant, every force, every microscopic variable is calibrated with impossible precision. This isn't just coincidence, it's the fine-tuning problem, one of the most profound puzzles in cosmology. Let's put it in perspective. The strength of gravity is balanced on a knife's edge. If it were just a fraction weaker, matter wouldn't clump together to form stars. A fraction stronger, and stars would burn out in mere millions of years, too quickly for life to evolve. Then there's the cosmological constant, which governs the expansion of the universe. Adjust it by 1 part in 10 to the power of 120, and reality either collapses or tears itself apart before the first atoms form. That's like throwing a dart across the observable universe and hitting a bullseye the size of a single atom. So how do we explain this cosmic precision? One camp argues it's pure luck, a statistical fluke in an otherwise lifeless multiverse. Imagine a lottery with infinite tickets, each representing a universe with random physical constants. We just happen to hold the winning ticket, the one where conditions align for galaxies, planets, and conscious observers. It's called the anthropic principle. The universe appears fine-tuned because we're here to notice it. In countless other realities, there's no one to wonder why things don't add up, but others see something more intentional. Could the universe's fine-tuning hint at deeper laws we haven't uncovered yet? Some physicists speculate about a theory of everything that would naturally explain these constants, like pieces of a puzzle snapping into place. String theory, for example, suggests higher dimensions might fix the values we observe, making life inevitable rather than accidental. And then there's the most controversial idea, that fine-tuning points to some form of cosmic design, not necessarily a traditional creator, but perhaps an underlying intelligence or self-organizing principle woven into reality itself. The voids between galaxies might seem empty, but they're part of this delicate balance. These vast, dark regions aren't just gaps, they're the negative space in the universe's grand design, sculpted by the same forces that set the stage for life. Without them, matter would be too densely packed, leading to catastrophic collisions and chaotic orbits. Yet even here, mystery lingers. Why are these voids so large? Why do galaxies cluster along invisible filaments, like dew on a spider's web? The answers might lie in the universe's earliest moments, when quantum fluctuations etched their patterns into the fabric of spacetime. What's clear is this: the fine-tuning problem forces us to confront the sheer improbability of our existence. Whether through multiverses, undiscovered physics, or something even stranger, the universe whispers that we're part of something far grander than chance. And as we peer into those dark voids, we're not just studying empty space, we're reading the fingerprints of whatever or whoever set the cosmic scales. Between the glittering threads of galaxies and clusters lies the universe's best-kept secret, cosmic voids, regions so vast and empty they defy comprehension. Picture a single void stretching over 300 million light-years, a bubble of near nothingness so large it could swallow thousands of Milky Ways without a trace. These aren't just gaps, they're the universe's silent giants, shaping the cosmic web in ways we're only beginning to grasp. And their existence throws our understanding of structure into question, because according to the Big Bang's afterglow, matter should be spread far more evenly. So why are these deserts of space so staggeringly empty? The answer might lie in the universe's infancy. During the first moments after the Big Bang, quantum fluctuations, tiny ripples in density, imprinted themselves on the fabric of spacetime. As the cosmos expanded, these ripples grew, with denser regions collapsing into galaxies and clusters, while the emptier patches stretched into voids. It's like watching dough rise. Where there's a tiny air pocket, it balloons into a cavern as the dough expands. But here's the twist: voids aren't completely barren. They contain a sparse sprinkling of rogue galaxies, drifting like ships in an ocean with no shore. And these isolated galaxies behave strangely, spinning faster and forming stars differently than their crowded counterparts. It's as if the void itself is whispering to them, altering their destiny through some unseen influence. Dark energy adds another layer to the mystery. As the universe accelerates, voids are growing faster than denser regions, their emptiness magnified by the repulsive force pushing space apart. Some theorists suggest voids might even be the primary drivers of cosmic expansion, their gravitational push outweighing the pull of matter-rich areas. Imagine blowing bubbles in a glass of soda. The emptier the bubble, the faster it grows, distorting the liquid around it. Could voids be the universe's way of revealing dark energy's true nature? Then there's the spine-chilling possibility that voids aren't entirely natural. Could they be scars from collisions with other universes in the multiverse, like bruises left by a cosmic fist? Or perhaps they're the fingerprints of exotic physics regions where dark matter behaves differently, or where dimensions we can't perceive are subtly warping reality. The largest void ever discovered, the Boötes void, spans 330 million light-years and contains just 60 galaxies. To put that in perspective, our local neighborhood would pack over 10,000 galaxies into the same space. What force could carve such a vacuum? Mapping these voids is like tracing the negative space in a sculpture. It reveals the shape of what's missing. Astronomers use redshift surveys, charting millions of galaxies to outline the voids between them, while simulations recreate their growth from the Big Bang to today. Each new dataset peels back another layer, showing how voids twist the light passing through them, creating subtle distortions in the cosmic microwave background. They're not passive holes, they're active players in the universe's evolution, sculpting the paths of galaxies and redirecting the flow of cosmic rivers. Yet for all their influence, voids remain eerily silent. If intelligent life exists within one, its night sky would be almost black, with no neighboring galaxies to light the darkness. The concept alone challenges our anthropic biases. What if we're the outliers and most civilizations arise in the dense filaments, never knowing the loneliness of the void? As we probe deeper, these empty expanses become a mirror, reflecting how much we still don't understand about the universe's architecture. They're not just absences, they're clues to dark energy's grip, to the Big Bang's echoes, and perhaps to forces we've yet to name. And that realization leads us to the next mystery, where the universe's scaffolding reveals its most enigmatic flaw. Our galaxy isn't drifting through space aimlessly, it's being pulled. At over 600 kilometers per second, the Milky Way and its neighbors are hurtling toward something colossal, something hidden behind a veil of cosmic dust so thick we've barely glimpsed its outline. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it bends the paths of entire galaxies like a cosmic magnet. And yet, even after decades of searching, we still don't know exactly what it is. The story begins in the 1970s when scientists mapping the universe's large-scale structure noticed something odd. Galaxies in our local group, including Andromeda and the Milky Way, weren't just expanding with the universe, they were all streaming toward the same patch of sky near the constellation Centaurus. This motion defied expectations. The Big Bang's afterglow suggested matter should be spreading evenly, like raisins in rising dough. Instead, something unseen was tugging us off course. The culprit, a gravitational force equivalent to tens of thousands of Milky Ways, concentrated in a region obscured by our own galaxy's dusty disk. Early theories pointed to the Norma cluster, a massive gathering of galaxies about 250 million light-years away. But calculations soon revealed its gravity was far too weak to explain the pull. The true source lay deeper, in a mysterious region dubbed the Great Attractor. Then, in the 2010s, an even larger structure came into focus, the Laniakea supercluster, a sprawling web of galaxies spanning 500 million light-years, with the Great Attractor at its heart. Think of it as a cosmic whirlpool, with galaxies flowing like rivers toward its hidden core. Yet the mystery only deepens. Even Laniakea's immense mass can't fully account for the observed motion. Some researchers speculate that an even grander structure lurks beyond, perhaps the Shapley supercluster, the most massive concentration of galaxies in the observable universe, lying another 600 million light-years past the Great Attractor. Others wonder if dark matter is clumped in ways we can't yet detect, or if exotic physics is at play. Could there be a flaw in our understanding of gravity itself, a hidden variable warping space on scales we're only beginning to probe? The challenge isn't just scientific, it's observational. The Milky Way's dusty bulge blocks our view of the Great Attractor's central regions, like trying to spot a mountain through fog. Infrared and radio telescopes which pierce through dust have mapped thousands of previously hidden galaxies in this zone, but the full picture remains elusive. Every new observation adds another piece to the puzzle, revealing filaments of dark matter, streams of wandering stars, and clusters colliding in slow motion. What's clear is this: the Great Attractor isn't just a curiosity. It's a reminder that the universe operates on scales we're still struggling to measure, let alone comprehend. As we chart its influence, we're not just mapping a destination, we're tracing the unseen currents that shape our cosmic journey. And that path leads us to an even more primordial mystery, etched in the oldest light the universe has to offer. Imagine holding a photograph of the universe as a newborn, a snapshot taken just 380,000 years after the Big Bang. That's precisely what the cosmic microwave background gives us, the oldest light in existence, a faint glow stretching across the entire sky. But within this primordial portrait lies a bizarre anomaly, a patch of cold, roughly the size of a fist held at arm's length, where the temperature dips mysteriously below the surrounding warmth. Scientists call it the CMB cold spot, and its existence challenges everything we thought we knew about the cosmos. At first glance, the cold spot might seem like a minor irregularity in an otherwise smooth background. But the numbers tell a different story. Statistical analysis reveals there's only a 1 in 200 chance such a feature would appear randomly in our universe. So what could carve a cosmic chill into the fabric of reality? One theory points to an enormous supervoid, a region of space so empty it stretches over 1 billion light-years across. As light travels through these voids, it loses energy like a hiker trudging uphill, resulting in a slight cooling effect. But here's the catch: even the largest known voids can't fully explain the cold spot's extreme temperature drop. The math simply doesn't add up. This discrepancy has led to a far more radical explanation, one that brushes against the edges of science fiction. Some physicists suggest the cold spot might be a bruise left by a collision with another universe. In the multiverse scenario, where countless bubble universes float in a higher dimensional space, our cosmos could have bumped into a neighboring one during its inflationary phase. The energy released in that collision would leave a distinct imprint, a circular region of unusual coldness in the CMB. It's as if we're staring at a fingerprint pressed into the universe's earliest moments, evidence of something beyond our cosmic horizon. Yet not everyone is convinced. Skeptics argue the cold spot could still be a statistical fluke, a cosmic illusion amplified by our limited perspective. Others propose exotic physics, like textures, defects in spacetime structure left over from the universe's rapid expansion. These theoretical knots in the fabric of reality could warp light in ways that mimic cooling. Meanwhile, advanced simulations scramble to recreate the cold spot's properties, testing whether known physics can birth such an anomaly without invoking parallel universes. The stakes are higher than they seem. If the cold spot truly is a multiverse signature, it would be the first tangible evidence that our universe isn't alone. Telescopes like the Planck satellite have scrutinized this icy patch for decades, mapping its subtle polarization patterns and temperature gradients. Future observatories with even sharper resolution might detect secondary signatures, ripples, or polarization twists that could confirm or debunk the collision theory. Until then, the cold spot remains a tantalizing enigma, a whisper from the universe's infancy that we're still learning to decipher. And that uncertainty leads us to a question even more fundamental than where we are when we are. Is time a fixed arrow, or could it be just another layer of the cosmic illusion? We take time's forward march for granted. Eggs crack but never uncrack. Candles melt but never reform. Memories accumulate but never erase. This relentless one-way flow is so ingrained in our experience that we call it the arrow of time. But peel back the cosmic curtain and you'll find something astonishing. Nothing in the fundamental laws of physics actually demands time must move forward. At the quantum level, equations work perfectly whether time runs forward or backward. So why does our universe stubbornly insist on this singular direction? The answer might lie in one of physics' most profound concepts, entropy. Picture a sandcastle on a beach. Left alone, wind and waves will inevitably reduce it to a shapeless mound, a transition from order to disorder. This is entropy in action, the universe's tendency toward chaos. The second law of thermodynamics states that entropy always increases in closed systems, creating an irreversible gradient from past to future. Scramble an egg and you've increased the entropy of that system. Burn a log and the ashes will never spontaneously reassemble into wood. Entropy gives time its apparent arrow by providing a cosmic before and after, a progression we can't undo. But here's where quantum mechanics throws a wrench into this tidy explanation. At the subatomic level, particles don't seem to care about time's direction. Electrons orbit atoms just as happily whether time flows forward or backward. Some quantum processes, like the interaction of certain mesons, even appear temporarily reversible. This has led physicists like Julian Barber to propose that time might be an illusion, a byproduct of our limited perspective, in a universe where every moment exists simultaneously. Think of a film strip. Each frame is eternally present, and our consciousness simply moves through them, creating the sensation of flow. The plot thickens when we examine black holes. These cosmic anomalies appear to violate entropy's rules by concentrating vast amounts of information into infinitesimal points. Some theories suggest that inside a black hole, spacetime becomes so warped that cause and effect might tangle, allowing events to unfold backward relative to our perspective. And if the universe eventually collapses in a big crunch, could entropy reverse, making broken teacups reassemble and scattered stardust coalesce into stars? Perhaps most mind-bending is the quantum entanglement phenomenon we explored earlier. When particles remain mysteriously linked across space, their connection seems to transcend time entirely. Experiments have shown that measuring one entangled particle can retroactively affect its partner's state, as if the future were reaching backward to tweak the past. This has led to radical proposals like the two-state vector theory, where every quantum event is influenced by both past and future conditions simultaneously. So is time's arrow an unbreakable law or a cosmic habit? The answer might lie in the universe's earliest moments. During the Big Bang, an unimaginably low entropy state was created, a perfect order that's been unraveling ever since, like a wound-up spring slowly releasing. But why did the universe begin in such an ordered state? Some theorists point to inflation, that explosive expansion in the first fraction of a second, as the ultimate entropy setter. Others speculate our arrow of time might be entangled with a parallel universe where time flows opposite to ours, balancing the cosmic books. As we probe deeper, even everyday experiences challenge our assumptions. Memories only record the past, but could a being with reversed entropy remember the future? The heat death of the universe, where entropy reaches maximum and all energy disperses, looms as times possible in-game unless quantum fluctuations or multiverse connections rewrite the rules. Laboratories are now testing these ideas with ultra-cold atoms and light beams, simulating time reversal scenarios that could reshape our understanding of reality's flow. The arrow of time isn't just a scientific puzzle, it's the foundation of human experience. every choice, every regret, every hope hinges on time's one-way current. Yet the universe whispers that this flow might be more fragile than we imagined, a local phenomenon in a grander reality where past, present, and future dance in ways we're only beginning to glimpse. And that realization pulls us toward our next mystery, the quantum realm, where particles flicker between existence and oblivion, and reality itself becomes a question of probability. If particles were actors, neutrinos would be the universe's ultimate method performers, shape-shifting mid-scene without a script. These ghostly particles, born in the hearts of stars and violent cosmic explosions, have a bizarre habit of changing identities as they streak through space. One moment they're electron neutrinos, the next muon or tau neutrinos, flickering between flavors like a cosmic chameleon. This vanishing act isn't just a quirk, it's a revolution in physics, proving these phantoms have mass when the standard model insisted they shouldn't. And that tiny discrepancy, it's a crack in the foundation of reality itself. To grasp why this matters, picture a spotlight sweeping across a dark stage. The beam represents a neutrino beam fired through Earth, say, from a particle accelerator in Switzerland to a detector under a mountain in Italy. By the time those neutrinos arrive, some have morphed into different types, as if the light changed colors mid-journey. This phenomenon, called neutrino oscillation, shattered decades of assumptions. The standard model, physics rulebook for particles, originally treated neutrinos as massless travelers. But oscillation proved they must have mass, however vanishingly small, to pull off such transformations. It's like discovering a shadow can weigh something after insisting it's just an absence of light. The implications ripple far beyond a textbook rewrite. Neutrinos are absurdly abundant. Trillions pass through your body every second, yet interact so weakly with matter that detecting them requires tanks of ultra-pure liquid buried deep underground, shielded from cosmic noise. Their elusiveness makes them cosmic messengers, carrying intel from environments too extreme for light to escape, like the cores of supernova or the swirling disks of black holes. Some theories even suggest neutrinos could be their own antimatter counterparts, a property that might explain why the universe favors matter over antimatter, a bias without which we wouldn't exist. But here's the real twist: neutrinos might be threading the dark universe together. Their tiny masses, still not precisely measured, could slot into theories of sterile neutrinos, hypothetical, even more elusive cousins that don't interact via any known force except gravity. If these exist, they could form the invisible scaffolding of dark matter, the missing mass holding galaxies intact. Imagine a cosmic internet where ordinary matter, stars, planets, us, is just the visible tip, while neutrinos and their kin are the hidden servers humming beneath the surface. The hunt for answers is as dramatic as the mystery itself. In Antarctica, the ice cube detector monitors a cubic kilometer of glacial ice for flashes of light created when neutrinos collide with atoms. In Japan, the Super Kamiokan facility, a colossal tank filled with 50,000 tons of ultra-pure water, waits for the faintest ripples from passing neutrinos. These experiments aren't just chasing particles. They're piecing together a puzzle where every new measurement forces us to redraw the map of fundamental physics. What makes neutrinos so thrilling is their refusal to fit neatly into our models. They're not just oddballs, they're messengers from the edge of understanding, whispering that the universe is far stranger than we've dared to imagine. And with every identity they swap mid-flight, they challenge us to rethink not just what exists, but how existence itself is woven together. This dance of the intangible leads us to the next enigma, one where the universe's architecture reveals a pattern so vast it rewrites the meaning of structure itself. The Hubble tension isn't just a scientific disagreement, it's a cosmic riddle threatening to unravel our understanding of the universe's expansion. Picture two teams of detectives measuring the speed of a car using different methods. One checks tire rotations, the other analyzes skid marks. Both are precise, yet their answers don't match. That's exactly what's happening in cosmology today. When scientists measure how fast the universe is expanding, a number called the Hubble constant, they get conflicting results depending on whether they study nearby supernova or the ancient afterglow of the Big Bang. The discrepancy isn't a small rounding error, it's a gaping hole in our cosmic blueprint, suggesting something fundamental is missing from the picture. Let's break down the methods causing this tension. The first approach, called the distance ladder, relies on blinking stars called Cepheid variables and exploding supernova in relatively nearby galaxies. These cosmic yardsticks let astronomers calculate distances and velocities, producing an expansion rate of about 73 kilometers per second per megaparsec. The second method examines the cosmic microwave background, that faint echo of the Big Bang captured by satellites like Planck. By analyzing tiny temperature fluctuations in this primordial light, physicists derive an expansion rate closer to 67. At first glance, the difference might seem trivial, but over cosmic distances, it snowballs into a chasm. If these numbers hold, it implies the universe is expanding nearly 10% faster than our best models predict. What could explain this mismatch? One tantalizing possibility is that an unknown force, something beyond dark energy, is tugging at the cosmos. Imagine pouring syrup into a bowl and watching it spread. If the syrup suddenly thins, it flows faster than expected. Could an unseen ingredient, perhaps a new type of dark energy or an interaction between dark matter and ordinary matter, be altering the universe's viscosity over time? Some theorists propose that dark energy isn't constant but evolves, growing stronger or weaker as the cosmos ages. Others speculate about primordial magnetic fields woven into spacetime or even relics from an earlier phase of the universe that left ghostly imprints on expansion. Then there's the more unsettling option. Our models might be fundamentally flawed. The standard cosmological model, Lambda CDM, has been remarkably successful at explaining everything from galaxy formation to the large-scale structure of the universe. But what if it's incomplete? Subtle errors in how we interpret the cosmic microwave background or overlooked biases in supernova measurements could be skewing the results. Some researchers suggest gravity itself might behave differently on cosmic scales, a deviation from Einstein's relativity that would require rewriting the rules of physics. It's like discovering your trusted compass works perfectly in your backyard but points askew when you hike a mountain. The stakes couldn't be higher. If the Hubble tension points to new physics, it would rank among the most profound discoveries since relativity or quantum mechanics. New telescopes like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope are poised to deliver ultra-precise measurements that could tip the scales toward one explanation or another. Meanwhile, labs are hunting for hypothetical particles that might mediate unseen forces, while simulations test whether exotic early universe conditions could leave fingerprints in today's expansion rate. What makes this mystery so thrilling is its humility. The universe isn't just expanding, it's refusing to conform to our expectations, leaving us with more questions than answers. And that's where science shines brightest, not in tidy solutions, but in the messy, glorious pursuit of truths that bend reality as we know it. As we peer deeper into this cosmic disagreement, we're not just measuring space, we're testing the very limits of what's possible. What if everything you see, the stars, your hands, even the thoughts in your mind, is just an elaborate simulation running on some unfathomable supercomputer? This isn't science fiction anymore. It's the simulation hypothesis, a theory so compelling that even some of the world's top physicists take it seriously. At its core, the idea suggests our universe might be an artificial construct, a hyper-realistic virtual reality engineered by an advanced civilization. And the evidence, it's hiding in plain sight, woven into the very fabric of reality itself. Start with the universe's mathematical precision. The laws of physics aren't just consistent, they're written in a language of perfect equations, from the elegant simplicity of Einstein's E equals mc squared to the fractal beauty of quantum field theory. It's as if someone designed a system with clean, efficient code, avoiding glitches or contradictions. Even the constants, the speed of light, the strength of gravity, are fine-tuned to absurdly precise values. Too perfect, some argue, to be accidental. Compare it to a video game. When programmers build a virtual world, they define rules like gravity or collision physics upfront. Our universe's flawless mathematical backbone could be the signature of a cosmic developer. Then there's quantum mechanics, where reality behaves less like a solid object and more like a pixelated rendering. Particles exist in multiple states until observed, as if the simulation conserves processing power by only rendering details when needed. The famous double-slit experiment shows particles acting as waves when unobserved, then snapping into definite positions the moment we look, like a game reducing resolution in areas the player isn't viewing. Even more bizarre is quantum entanglement, where particles instantly coordinate across vast distances, defying the speed of light. In a simulated universe, this could simply be two variables sharing the same memory address, updating in sync without physical interaction. But the most haunting clues might lie in the universe's limits. Just as a computer has processing constraints, frame rate lag, memory allocation, our reality has fundamental limits too. The Planck length, the smallest possible unit of space, could be the pixel size of the simulation. The speed of light, a hard-coded processing speed limit preventing the system from overloading. Even the holographic principle, which suggests all 3D reality might be encoded on a 2D surface, mirrors how modern video games use texture mapping to create depth without overburdening the GPU. Of course, skeptics counter with Occam's razor. Isn't it simpler to assume reality is, well, real? Yet the simulation hypothesis isn't easily dismissed. Philosopher Nick Bostrom's trilemma argues one of three must be true. Almost all civilizations self-destruct before reaching simulation capability. Advanced civilizations have no interest in creating ancestor simulations, or we're almost certainly living in one. Given humanity's own trajectory toward virtual worlds, from rudimentary games to budding metaverses, the third option feels uncomfortably plausible. So how could we test this? Some scientists propose hunting for glitches in the simulation, cosmic rounding errors in physical constants, or anomalies in high-energy particle collisions. Others suggest looking for computational signatures, like pixelation at the Planck scale or evidence the universe runs on a lattice-like grid. There's even a wild idea that if the simulation relies on finite processing power, extremely complex calculations might trigger detectable lag, like the universe skipping frames to keep up. Whether metaphor or reality, the simulation hypothesis forces us to confront profound questions. If we're in a simulation, what's its purpose? An ancestor simulation reconstructing history, an alien civilization's experiment, or something beyond our comprehension entirely? And if we one day create our own simulations, does that make us programmers or characters in an even deeper layer of the code? The universe's mysteries have always humbled us, but this one doesn't just challenge what we know, it questions what we are, and that uncertainty brings us to the next enigma. where the universe's energy reaches such extremes that even simulations might struggle to render them, the incomprehensible power of gamma-ray bursts. One moment space is silent, the next a flash of energy brighter than 500 million suns erupts from the void, lasting just milliseconds before vanishing without a trace. These are fast radio bursts FRB, some of the universe's most enigmatic signals, arriving from galaxies billions of light-years away with no obvious explanation. What could possibly unleash such staggering energy in the blink of an eye? The answer might rewrite our understanding of cosmic cataclysms or hint at something far more extraordinary. The first FRB was spotted in 2007, buried in archival data from a radio telescope in Australia. At first, astronomers dismissed it as a glitch, a blip in the instruments. But then more appeared, each a fleeting burst of radio waves packing as much energy as our sun emits in days. Some arrive solo, cosmic one-hit wonders. Others, like FRB 1211-2, repeat in unpredictable patterns, flickering on and off like a malfunctioning beacon. The sources, distant galaxies, some so far away their light has traveled for half the age of the universe to reach us. So what's behind these cosmic fireworks? One leading theory points to magnetars, neutron stars with magnetic fields so intense they could strip the electrons from your atoms at 1,000 kilometers away. When these stellar corpses undergo starquakes, sudden cracks in their ultra-dense crusts, they might unleash bursts of energy visible across the cosmos. Imagine snapping a rubber band stretched to its limit, but on a scale where the snap unleashes a shockwave powerful enough to ripple through intergalactic space. But there's a twist. Some FRBs pulse with a regularity that defies natural explanations, like cosmic metronomes ticking with eerie precision. This has led to inevitable, if controversial, speculation about artificial origins. Could these be interstellar lighthouses, engineered by advanced civilizations to navigate the void or broadcast their existence? The idea isn't as far-fetched as it sounds. In 1974, we famously beamed the Arecibo message toward a star cluster, a deliberate radio hello to any potential listeners. If aliens had similar technology, their signals might resemble FRBs to distant observers. Yet the universe often outpaces our wildest imaginations. Another possibility involves colliding neutron stars or black holes, cosmic smash-ups so violent they warp spacetime itself, sending shockwaves through the surrounding plasma. These events could generate FRBs like sparks from a celestial anvil. There's even a hypothesis linking FRBs to cosmic strings, hypothetical defects in spacetime left over from the Big Bang, vibrating like guitar strings and releasing bursts of energy as they snap. The real breakthrough came in 2020, when astronomers traced an FRB to a magnetar within our own galaxy, confirming at least some bursts originate from these magnetic monsters. But the mystery is far from solved. Why do some repeat while others vanish forever? How can they be so bright? And why do a handful exhibit bizarre polarization patterns, as if their signals have been twisted by traversing vast cosmic magnetic fields? Every new detection adds layers to the puzzle. Radio telescopes like CHIME in Canada now catch dozens of FRBs monthly, mapping their arrival directions and hunting for patterns. Some bursts arrive with a dispersion sweep, a telltale smear of frequencies caused by traversing intergalactic gas, offering clues about the invisible matter they've passed through. Others come with sideband signals like echoes hinting at turbulent environments near their sources. What makes FRBs so captivating isn't just their mystery, it's their potential. These flashes could be cosmic tools, probing the tenuous gas between galaxies or revealing the universe's hidden structure. They might even help solve the missing matter problem, as their dispersion measures how much stuff they've traveled through. And if against all odds they are artificial, the implications would dwarf every discovery in human history. For now, FRBs remain cosmic postcards from the edge of understanding, each one scribbled in a language we're still learning to read. Whether natural or engineered, they remind us the universe is far from silent. It's shouting in a code we've only just begun to crack. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars, many hosting planets in the perfect Goldilocks zone for life. Given those odds, the cosmos should be teeming with civilizations, their radio signals crisscrossing the void like a bustling interstellar internet. Yet when we listen, all we hear is silence. This eerie absence is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" It's one of the most unsettling mysteries in science, not because of what we've found, but because of what we haven't. Let's break down the numbers. Conservative estimates suggest there are at least 100 billion planets in our galaxy, alone capable of supporting liquid water. Even if life arises on just 1 in a million of those, the Milky Way should still host 100,000 civilizations, and given the galaxy's age 13 billion years, many would have had ample time to develop technology far beyond ours, perhaps colonizing entire star systems. So why no radio transmissions, no megastructures, no fleeting visits? The possibilities range from humbling to terrifying. One explanation is the Great Filter, a hypothetical barrier that prevents life from progressing to interstellar communication. It could lie in our past. Perhaps the leap from simple chemistry to self-replicating life is astronomically rare, making Earth a cosmic fluke. Or worse, the filter might await us in the future. Nearly every advanced civilization could self-destruct through nuclear war, runaway AI, or ecological collapse before achieving interstellar travel. This would mean the silence isn't a mystery but a warning, a galactic graveyard whispering what happens to societies like ours. Then there's the zoo hypothesis, the idea that advanced civilizations intentionally avoid contact, observing us like animals in a cosmic wildlife preserve. Imagine ants in a rainforest, unaware of the biologists watching from a distance. If true, alien societies might follow strict protocols to avoid contaminating our development, waiting until we reach some ethical or technological threshold before saying hello. Alternatively, we could be hopelessly primitive to them, like microbes trying to hail a passing jetliner. Technological limitations also play a role. Our radio signals have only traveled about 100 light-years from Earth, a tiny bubble in a galaxy spanning 100,000 light-years. Alien transmissions might use communication methods we can't yet detect, like neutrino beams or quantum entanglement. Or perhaps civilizations rapidly transition to inward-focused virtual realities, losing interest in physical exploration. A post-biological society might dwell in matryoshka brains, Dyson spheres enclosing stars to power planet-sized supercomputers, too absorbed in digital existences to broadcast outward. But the darkest answer is that space is far more dangerous than we realize. Gamma-ray bursts, asteroid impacts, or predatory AI could sterilize galaxies in waves, leaving only fleeting windows for civilizations to arise. Some theorists even suggest that advanced life inevitably creates its own existential threats, like accidentally triggering vacuum decay, a catastrophic phase transition that rewrites the laws of physics in an expanding bubble of destruction. Yet amid these grim scenarios, there's a spark of hope. New telescopes like the James Webb and upcoming projects like the Square Kilometre Array are scanning exoplanet atmospheres for biosignatures, chemical traces of life. Breakthrough Listen analyzes millions of radio channels for artificial signals. Even our own probes, like Voyager, carry messages for any civilization that might find them. The Fermi Paradox isn't just a question, it's a mirror. In searching for aliens, we're really asking what we might become, and whether intelligence is a candle flickering in the dark or a wildfire destined to illuminate the cosmos. And that uncertainty pulls us toward the vacuum of space itself, not as emptiness, but as a seething quantum foam where particles blink in and out of existence, defying every intuition about what nothing really means. Empty space isn't empty. That's the first shocking truth about vacuum energy. Even in the deepest voids between galaxies, where not a single atom lingers, space itself crackles with an invisible energy, a seething quantum foam where particles flicker in and out of existence like sparks in the dark. According to quantum theory, this vacuum energy should be unimaginably powerful, packing enough punch to rip atoms apart and warp space-time beyond recognition. Yet when we measure it, the energy of empty space is eerily weak, a whisper where physics predicts a scream. This discrepancy isn't just a minor hiccup, it's the cosmological constant problem, a gulf between prediction and reality, so vast it threatens to upend our understanding of the universe's very fabric. To grasp the scale of the mystery, imagine a pendulum suspended in midair. Quantum mechanics calculates that the pendulum should swing with the force of a hurricane, driven by the relentless popping of virtual particles in the vacuum around it. But in reality, it barely trembles. The math says empty space should weigh the universe down with an energy density of 10 to the power of 120 times what we observe. That's a 1 followed by 120 zeros, a number so large it defies metaphor. If the vacuum energy matched these predictions, galaxies would have been torn apart before they even formed. Reality, somehow, has dialed this force down to almost nothing. Why? One haunting possibility is that we're missing a cosmic cancellation mechanism, some undiscovered symmetry or interaction that perfectly balances the vacuum's fury. Picture two mighty waves crashing into each other, their peaks and troughs aligning to leave the water eerily calm. String theory proposes such a balance might exist in hidden dimensions, where vibrations we can't perceive cancel out the vacuum's energy. But this solution feels unnervingly fine-tuned, like balancing a pencil on its tip for billions of years. Others suggest the vacuum's energy isn't constant but decays over time, starting strong in the early universe and fading to near silence today. It's as if the cosmos had a wild youth, then settled into middle-aged quiet. Then there's the multiverse angle. If countless universes bubble into existence with random vacuum energies, most would collapse or tear themselves apart instantly. Only in rare bubbles where the energy happens to be absurdly weak could galaxies and life arise. We might live in the 1 in a trillion universe where the numbers lined up just right. This anthropic explanation dodges the question of why the energy is small, settling for how we ended up observing it. But for many scientists, it's a philosophical surrender, swapping a physical mechanism for statistical luck. The vacuum's silence might also hint at something deeper. That empty space isn't fundamental, but emerges from a more basic layer of reality. Think of ice forming on a lake. The crystalline structure seems solid, but it's really just water molecules arranging themselves in a pattern. Similarly, spacetime's energy could be a collective effect of some underlying quantum network. Its apparent hush the result of hidden interactions we've yet to uncover. Experiments with ultra-cold atoms and quantum simulators are testing this idea, crafting lab-scale models where empty space behaves in ways that defy classical intuition. What's at stake isn't just academic. If the vacuum's energy were slightly stronger, dark energy, the force accelerating the universe's expansion, might have dominated earlier, preventing stars and galaxies from ever forming. Alternatively, if we could tap into vacuum energy's predicted potential, it would offer a power source beyond fusion, even beyond antimatter. The catch: we'd need to understand why it's so weak first. Some theorists speculate that vacuum fluctuations might hold the key to warp drive concepts, bending spacetime in ways that sidestep light speed limits. But until we solve the cosmological constant problem, such ideas remain science fiction. The mystery humbles us. The vacuum isn't a static stage, it's a dynamic, writhing thing. Its energy a puzzle written into the universe's blueprints. Whether the answer lies in undiscovered physics, cosmic accidents, or layers of reality we can't yet perceive, one thing is clear: empty space is anything but simple. And as we probe deeper, we're not just studying nothingness, we're decoding the hidden rules that let somethingness exist at all. Einstein called it spooky action at a distance, a phenomenon so bizarre it made him question the foundations of quantum mechanics itself. The Fermi Paradox, named after Einstein, Podolsky, and Rosen, challenges one of our most basic assumptions about reality: that nothing, not even information, can travel faster than light. Yet when two particles become entangled, measuring one instantly determines the state of its partner, no matter how far apart they are, not at the speed of light. Not with any delay, instantly. It's as if the universe has a hidden hotline connecting particles across cosmic distances, bypassing spacetime entirely. Here's what makes this so revolutionary. Imagine you have a pair of magical dice, one in New York, the other in Tokyo. Roll the New York die and it lands on 4. At that exact moment, the Tokyo die also shows 4 without any signal passing between them. This isn't just a thought experiment. Real-world tests, like the groundbreaking experiments by Elaine Aspect in the 1980s, have confirmed entanglement's eerie precision. Photons separated by hundreds of kilometers sync their properties: polarization, spin, even momentum, faster than a beam of light could bridge the gap. The math says it happens at least 10,000 times the speed of light. So how does it work? One radical answer is that the particles aren't truly separate to begin with. Quantum mechanics suggests that until measured, entangled particles exist in a shared state, a single mathematical entity spread across space. Measuring one collapses the entire system, like plucking a single string on a guitar and hearing the whole instrument resonate. There's no signal racing through space because, in a quantum sense, there's no distance to cross. The universe, at its deepest level, might not be a collection of isolated objects, but a vast, interconnected network where separation is an illusion. But this throws locality, the idea that objects are only influenced by their immediate surroundings, out the window. Einstein hated this. He believed reality should be local, with no mysterious long-distance links. To save locality, some theorists propose hidden variables, unseen factors predetermining particle states from the moment they entangle, but experiments keep ruling this out. Others suggest retrocausality, that future measurements somehow reach backward in time to influence past interactions. Picture ripples in a pond flowing upstream to disturb the stone that cast them. The most mind-bending possibility: entanglement might reveal spacetime's true nature. In holographic theories, the three-dimensional world we see could be a projection of information encoded on a two-dimensional surface. Entangled particles wouldn't need to communicate because their connection exists outside spacetime, like 2 points on a sheet of paper, realizing they're actually part of the same sentence. Even black holes, those cosmic shredders, might preserve information through entanglement, with particles inside and outside the event horizon remaining mysteriously linked. The implications are staggering. If entanglement defies locality, it could rewrite our understanding of cause and effect. Quantum computers already harness this phenomenon to perform calculations impossible for classical machines. Future quantum networks might use entangled photons for unhackable communication, with satellites acting as cosmic switchboards. And if spacetime itself emerges from entanglement, as some theories suggest, we're not just studying particles, we're glimpsing the architecture of reality. Yet for all our progress, the central mystery remains. Entanglement feels less like a puzzle to solve and more like a cosmic clue, whispering that the universe's rulebook is far stranger than we imagined. And as we peel back its layers, we're forced to ask, if particles can transcend spacetime, what else might be possible? The cosmic microwave background should be the ultimate equalizer, a perfectly uniform afterglow from the Big Bang, the same in every direction. But when scientists mapped its subtle temperature variations, they stumbled upon something unsettling. The universe appears to have a preferred axis, like an invisible spine running through the cosmos. Dubbed the axis of evil, this alignment defies one of cosmology's sacred principles that the universe has no special direction, no center, no up or down. Yet the data refuses to cooperate. Hot and cold spots in the microwave background line up along this mysterious axis like beads on a string, whispering that the cosmos might be fundamentally lopsided. So what could explain this cosmic asymmetry? One possibility is that we're seeing the fingerprints of an ancient, universe-spanning force, perhaps a relic magnetic field from the Big Bang, or a primordial turbulence frozen into spacetime itself. Picture a pot of boiling water suddenly frozen mid-bubble. The patterns left behind would tell a story of the chaos that came before. Alternatively, the axis might trace the path of dark energy's influence, a shadow of how this mysterious force stretches space unevenly across the universe. But the most radical interpretation is that we're glimpsing something beyond our observable universe. Just as a ship on the ocean can't see the entire globe but might detect Earth's curvature in subtle shifts, the axis could be a signpost pointing to structures or forces outside our cosmic horizon. Imagine our universe as a bubble floating in a vast multiverse foam. Collisions with neighboring bubbles could have left scars in the microwave background, tilting the cosmos in ways we're only beginning to decode. Critics argue the axis might be an illusion, a statistical fluke, or an artifact of how we process the data. Yet as measurements grow more precise, the anomaly persists, gnawing at the edges of our understanding. If confirmed, it would force us to rewrite cosmology's rulebook, abandoning the comforting idea that the universe is the same everywhere and embracing a reality that's fundamentally uneven. Which brings us to an even more fundamental question: what is nothingness? We think of empty space as pure absence, but quantum physics paints a far stranger picture. The vacuum of space isn't empty at all. It's a seething quantum foam where particles flicker in and out of existence, borrowing energy from the future to briefly take shape. This nothing holds more energy than all the stars and galaxies combined, locked in a dance of creation and annihilation that never ceases. Einstein's equations suggest that empty space can repel as well as attract, giving rise to dark energy's mysterious push. But why does the vacuum have energy at all? And why is it so weak compared to theoretical predictions? The answer might lie in hidden dimensions or undiscovered symmetries that cancel out the vacuum's fury. Or perhaps nothing is just a label for a state we don't yet understand, like calling the ocean empty because we can't see the life teeming within it. The deeper we probe, the clearer it becomes. Nothingness is the universe's most misunderstood ingredient. It's not the absence of things, but the stage upon which reality performs, a dynamic player in the cosmic drama rather than a passive backdrop. And if we ever unravel its secrets, we might find that the key to everything was nothing all along. Close your eyes and picture nothingness, a void so complete it lacks even the faintest whisper of matter, energy, or time. Now open them, because according to quantum physics, that perfect emptiness doesn't exist. The universe abhors a true vacuum. Even in the deepest reaches of space, where no star shines and no atom drifts, the void is alive with a seething dance of virtual particles. They flicker into existence for fractions of a second, borrowing energy from the future to briefly take shape before vanishing back into the quantum foam. This isn't poetic metaphor, it's measurable reality, proven by effects like the Casimir force, where two metal plates placed nanometers apart in a vacuum are pushed together by the pressure of these ghostly particles popping in and out of being outside them. So what is nothingness if not empty? The answer unravels one of physics' greatest illusions. The quantum vacuum isn't passive absence, it's a roiling substrate, a kind of cosmic canvas where reality's brushstrokes appear and disappear. Think of it like static on an old TV screen. What seems like blank noise is actually a storm of underlying activity. These quantum fluctuations aren't just theoretical quirks. They're the reason stars shine. In the sun's core, the vacuum's churn allows protons to overcome their mutual repulsion and fuse, igniting the nuclear fires that light our days. Without this empty space's hidden energy, the universe would be dark and lifeless. But here's the twist that bends the mind. The vacuum's energy density, when calculated using quantum theory, should be astronomically higher than what we observe, by a factor of 1 followed by 120 zeros. This discrepancy, called the cosmological constant problem, is the widest gulf between prediction and measurement in all of science. It's as if you calculated the ocean's depth to be the distance to the moon, then dipped a bucket and found only a teaspoon of water. Some theorists argue this points to undiscovered physics, perhaps hidden dimensions or symmetries that cancel out the vacuum's fury. Others invoke the multiverse. Maybe most universes drown in their own vacuum energy, and we just happen to inhabit a rare bubble where it's weak enough for galaxies to form. The stakes couldn't be higher. If the vacuum's energy were slightly stronger, dark energy would have ripped apart the cosmos before life could arise. Slightly weaker, and gravity would have crushed everything back into a singularity. This fine-tuning suggests that nothing might be the universe's most carefully engineered ingredient. And if we ever learn to manipulate it, the implications would dwarf every technological revolution in history. Warp drives, theoretical designs like the Alcubierre metric rely on bending the vacuum structure to sidestep light speed limits. Unlimited energy, the zero-point energy locked in empty space, could power civilizations if we could tap it without destabilizing reality itself. Yet the deepest mystery isn't what nothingness contains, but what it is. Some theories suggest spacetime might emerge from quantum entanglement, meaning the vacuum isn't a static stage but a network of relationships. Others propose that what we call empty is actually a superfluid, a frictionless quantum sea where turbulence gives rise to particles like eddies in a stream. The more we probe, the clearer it becomes. Nothingness is the universe's foundational enigma, the silent architect of everything we see. So the next time you gaze at the night sky, remember this: the vast darkness between stars isn't empty. It's the universe's workshop, where the raw materials of reality are endlessly forged and unforged. And that realization leads us to an even more unsettling question. If nothingness is this rich, this dynamic, what else might be hiding in plain sight? Crossing the event horizon of a black hole should be a quiet affair, at least according to Einstein's general relativity. Step over that invisible boundary, and spacetime's gentle curvature would carry you inward, stretching you like taffy, but leaving you blissfully unaware of the point of no return. But quantum mechanics paints a far more violent picture. Lurking just inside the horizon, there might be a searing wall of fire, a cosmic kill switch that vaporizes anything daring enough to approach. This is the black hole firewall paradox, a collision of physics' two greatest theories that threatens to rewrite the rules of reality itself. The conflict starts with information. Quantum mechanics insists it can never be destroyed, only scrambled. Every particle, every interaction leaves an indelible mark on the universe. Yet black holes, those cosmic shredders, appear to erase information entirely as they evaporate via Hawking radiation. To resolve this, physicists propose that the event horizon isn't just a one-way street, it's a chaotic quantum processor, encoding swallowed data into the radiation it emits. But here's the catch. For this to work, particles just inside and outside the horizon must be entangled, their fates intertwined like threads in a tapestry. Enter the firewall. Quantum theory's monogamy rule says particles can't share entanglement freely. If Hawking radiation pairs are entangled with each other, they can't also be entangled with particles inside the black hole. The only solution: a catastrophic break, a discontinuity at the horizon where entanglement snaps like a rubber band, releasing enough energy to create a literal wall of ultra-high-energy particles. Imagine stepping through what you thought was a harmless doorway, only to be vaporized by a curtain of plasma hotter than a supernova. Relativity rebels at this idea. To an observer falling in, the horizon should feel like empty space, no fire, no drama. This principle, called equivalence, is the bedrock of Einstein's theory. But if firewalls exist, relativity fails at the very edge of black holes, forcing us to choose. Either quantum mechanics is wrong about information, or relativity is wrong about spacetime's smoothness. It's like discovering your two favorite maps of the world disagree on the location of an entire continent. Some theorists suggest a third path, that firewalls only form when someone tries to measure the paradox, a cosmic version of the observer effect. Others propose the horizon is a hologram, with all the black hole's information smeared across its surface like a cosmic QR code. Then there's the wild possibility that black holes have no interiors at all. What we perceive as a bottomless pit might be a flaw in spacetime, a frozen storm where time stalls indefinitely. The stakes, if firewalls are real, they'd be the universe's most brutal censorship system, erasing travelers before they could report what lies beyond. But if they're not, we're back to square one with information loss, forcing quantum mechanics to surrender its most sacred rule. Labs are tackling this with analog black holes using sound waves in superfluid helium or light in optical fibers to mimic event horizons. These tabletop cosmos might reveal whether firewalls are inevitable or just a glitch in our math. What makes this paradox so thrilling is its audacity. Black holes aren't just testing gravity or quantum theory, they're stress-testing reality's blueprint. And as we peel back the layers, we're left with a haunting question. If the rules break down here, where else might our cosmic map be lying to us? We think we know the dimensions of reality up and down, left and right, forward and backward, with time ticking steadily forward. But what if the universe is hiding entire realms just beyond our perception? String theory, one of physics' most ambitious frameworks, suggests there could be up to 11 dimensions, all curled into spaces so tiny they'd make an atom look like a galaxy. Imagine a garden hose stretched across a field. From a distance, it appears as a simple line, a one-dimensional object. But up close, you see its surface curves into a second dimension, a hidden cylindrical world. Now shrink that idea by a factor of a trillion. and you've got the extra dimensions that might shape everything from gravity's weakness to the very fabric of spacetime itself. The math behind this isn't just speculative, it's a necessity for string theory to work. For the equations to balance, strings, the theoretical vibrating filaments that replace particles, need more room to oscillate than our familiar 4 dimensions provide. Picture a guitar string. It can produce different notes depending on how it vibrates. Similarly, the properties of particles, their mass, charge, even the forces they feel might depend on how strings wiggle through these higher dimensional landscapes. Some theories propose that gravity, oddly weak compared to other forces, might actually be spilling into these extra dimensions, its strength diluted across unseen directions. But how could we ever detect something so infinitesimal? Particle colliders like the Large Hadron Collider hunt for clues by smashing protons together at near light speeds, hoping to glimpse energy vanishing into hidden dimensions like marbles rolling into invisible grooves. Other experiments search for deviations in gravity at microscopic scales, where extra dimensions might subtly alter the inverse square law we've relied on since Newton. And if these dimensions exist, they could be anything from simple loops to intricate Calabi-Yau manifold shapes so complex they're described by equations with thousands of terms, yet potentially governing the universe's deepest symmetries. The implications are staggering. If confirmed, extra dimensions would rewrite not just physics but our very understanding of reality's architecture. Dark matter could be ordinary matter trapped in a parallel brane, a slice of higher dimensional space just out of reach. The Big Bang might have been a collision between brains in a multidimensional cosmos. Even consciousness itself, some far-out theories suggest, could arise from processes woven through these hidden layers. Yet for all their promise, extra dimensions remain elusive. Critics argue they're untestable mathematical constructs, modern-day epicycles invented to preserve a beautiful but unproven theory. Others counter that absence of evidence isn't evidence of absence after all. Neutrinos once seemed equally fantastical. What's undeniable is that our 4-dimensional intuition is a poor guide to the universe's true complexity. The cosmos has a habit of being stranger than we imagine, and stranger than we can imagine, which makes our next mystery all the more provocative. The speed of light, long considered the universe's ultimate speed limit, might not be as absolute as we think. Einstein's cosmic speed limit, the idea that nothing can outrace light, has stood as one of physics' most sacred rules for over a century. But what if the universe has loopholes? Enter tachyons, hypothetical particles born already moving faster than light, their existence dangling a tantalizing question. Could reality's blueprint accommodate speedsters that flout relativity's most famous law? The implications aren't just about velocity, they'd tear open the fabric of causality itself, turning science fiction into potential science fact. Tachyons don't just break the light-speed barrier, they treat it like a starting line. Unlike ordinary matter, which needs infinite energy to approach light speed, tachyons would lose energy as they accelerated, their speed increasing as their energy dropped towards zero. Picture a cosmic speedboat that goes faster the less fuel you give it, an absurd inversion of everything we know. And here's the twist: relativity doesn't technically forbid faster than light travel. It just says nothing can accelerate past light speed. Tachyons sidestep this by existing permanently on the other side of that barrier, like a fish that's always swum deeper than any diver could reach. But with this defiance comes chaos. If tachyons exist, they'd warp causality like a pretzel. Their superluminal speed could allow them to arrive before they're emitted, creating time loops where effect precedes cause. Imagine a tachyon signal sent to your past self warning of an accident, a paradox where the warning creates the future that sends it. Einstein's equations suggest tachyons would experience time backward, living their lives from death to birth. It's the ultimate grandfather paradox, where a tachyon interaction might erase the very conditions that created it. So why haven't we found them? Experimental searches have turned up empty. Particle colliders hunt for anomalous track signatures of high-speed particles that deposit energy backward along their path. Cosmic ray detectors scour the skies for ultra-fast streaks that might betray a tachyon's passage. Even quantum field theories allow for tachyon-like fields, though these typically signal unstable systems rather than actual particles. Some theories suggest tachyons, if real, might be confined to higher dimensions or exist only as virtual particles, flickering in and out of reality too quickly to catch. Yet the math refuses to dismiss them entirely. Certain string theory models permit tachyon states, interpreting them not as particles but as instabilities in spacetime's fabric, like cracks in cosmic ice. Others propose tachyons might be dark matter candidates, their elusive nature explaining why they've evaded detection. There's even a wild hypothesis that the Big Bang's inflationary expansion was triggered by a tachyon field collapsing. It's faster-than-light energy morphing into the matter and radiation we see today. The real puzzle isn't just whether tachyons exist, it's what their absence says about the universe. Why does reality seem to enforce light speed as a barrier? Is it protecting causality, preventing time travel paradoxes that would unravel logic itself? Or is it hinting at a deeper structure where faster-than-light phenomena are possible but locked behind physics we've yet to uncover? For now, tachyons remain ghosts in the equations, a thrilling what if that challenges our assumptions. They remind us that the universe's rules might be more flexible than they appear, waiting for the right key to unlock their secrets. And that uncertainty propels us toward an even more profound mystery: the quantum realm's most defiant rule breakers, particles that don't just bend the laws of physics, they rewrite them on the fly. Imagine the universe as a movie screen. What we perceive as a rich, three-dimensional world might just be a dazzling projection from a hidden two-dimensional surface. This is the holographic principle, a radical idea born from black hole physics that suggests reality isn't what it seems. When scientists calculated how much information a black hole can hold, they made a startling discovery. The maximum data it can store isn't determined by its volume but by its surface area. It's as if every star, planet, and particle that falls into a black hole gets compressed into a flat, encoded image painted on its event horizon, like a cosmic barcode. This revelation led to an even wilder possibility. What if our entire universe operates the same way? The holographic principle proposes that the three-dimensional reality we experience, the depth of space, the texture of matter, even the flow of time, might be a grand illusion, a hologram generated from a two-dimensional boundary at the edge of existence. Picture a snow globe, but instead of a scene inside, the entire world is painted on its inner surface, and we're just shadows cast by that artwork. The math behind this isn't just speculative, it's shockingly precise. In the 1990s, physicist Juan Maldacena discovered a concrete holographic duality, linking a theoretical five-dimensional universe to a four-dimensional boundary. Though abstract, this model showed that events in the higher dimensional space could be perfectly described by equations operating on the lower dimensional surface, like a cosmic version of how a credit card's chip holds all the information needed to reconstruct your account. If this duality holds for our universe, it would mean every event, every particle, even your thoughts right now, are pixels in a vast cosmic projection. But how could flat information manifest as a 3D world? Think of your smartphone screen. Though it's only two-dimensional, the right combination of pixels creates the illusion of depth, a parallax effect that fools your brain. The holographic principle suggests spacetime might work similarly, with quantum entanglement acting as the pixels linking the surface layer to the volumetric illusion. Every time particles interact, they're updating the cosmic display, like a continuous rendering engine for reality. The implications rewrite the nature of time itself. If the universe is holographic, time might not flow like a river but emerge from how information updates on the boundary layer. Your sense of past, present, and future could be like a film strip's frames, each moment eternally encoded with your consciousness moving through them. This aligns with quantum gravity theories where time isn't fundamental but derived, a side effect of deeper, timeless physics. Critics argue the holographic principle remains untested, a beautiful metaphor without empirical proof. Yet experiments are creeping closer. Fermilab's holometer searched for quantum fuzziness in spacetime, a pixelation that would betray its holographic nature. Future quantum gravity probes might detect noise patterns matching a two-dimensional information limit. Even black hole mergers, by studying how their event horizons store information during collisions, could reveal holographic signatures in gravitational waves. Whether metaphor or reality, the holographic principle forces a humbling epiphany. The universe's true architecture might be nothing like what our senses perceive. The solidity of matter, the vastness of space, the arrow of time, all could be shadows on the wall of a deeper, stranger cosmos. And if that's true, what other illusions might we be mistaking for reality? If you've ever dreamed of a perpetual motion machine, something that cycles endlessly without energy input, prepare to have your mind blown. Time crystals aren't science fiction, they're real, and they defy one of physics' most sacred laws, the second law of thermodynamics. Unlike every other structure in the universe, which inevitably succumbs to entropy and decay, time crystals exist in a state of perpetual recurrence, their atomic patterns repeating not in space but in time. Imagine a snowflake that doesn't just sit frozen in a symmetrical shape, but one that pulses, rewinds, and pulses again forever without ever losing energy. This isn't magic, it's quantum mechanics at its most bewildering. The idea was first proposed by Nobel laureate Frank Wilczek in 2012, met with skepticism until experiments a few years later proved their existence. Here's how they work. Ordinary crystals, like diamonds or quartz, have atoms arranged in repeating spatial patterns. Time crystals take this further. Their atomic structures oscillate between configurations at fixed intervals, like a metronome ticking without being wound. The kicker: these oscillations don't require energy. They're the universe's first example of a system that achieves non-equilibrium stability, a paradox where motion persists indefinitely without violating energy conservation. It's as if the cosmos carved out a loophole in its own rulebook. But how? The secret lies in quantum entanglement and a phenomenon called many-body localization. In a normal system, energy disperses until everything reaches a uniform, boring equilibrium. Think of hot coffee cooling to room temperature. Time crystals avoid this fate because they're entangled particles locked together in a dance so coordinated they can't dissipate energy outward. Picture a stadium wave that keeps circling the crowd long after the fans have stopped cheering, sustained purely by the crowd's interconnected rhythm. The implications are staggering. If time crystals can maintain coherence without energy input, they might revolutionize quantum computing, where fragile quantum states usually crumble in microseconds. Laboratories are already embedding them in quantum systems to test their potential as unshakable memory units. But the bigger puzzle is cosmic. Could time crystals hint at deeper symmetries woven into spacetime itself? Some theorists speculate they might be relics from the early universe, quantum fossils carrying echoes of conditions before time, as we know it began. Others wonder if they're evidence of hidden dimensions, their oscillations resonating with frequencies beyond our perception. Yet the most tantalizing question remains, are time crystals a quirk of quantum engineering, or do they exist naturally in the wild? Some researchers propose that neutron stars' ultra-dense stellar corpses with insane magnetic fields might harbor time crystalline phases in their cores. Even dark matter, that elusive cosmic glue, could have time crystalline properties, its particles cycling through states in an eternal, invisible waltz. Time crystals don't just challenge our understanding of matter, they force us to rethink what time actually is. In a universe where entropy dictates the arrow of time, these structures flicker outside that flow, hinting at layers of reality where time might loop, stutter, or even run backward. They're not just curiosities, they're whispers from the quantum void, suggesting the cosmos has rhythms we've only begun to sense. And as we decode their secrets, we might find that perpetual motion wasn't impossible after all. We just hadn't looked deep enough into the quantum fabric of existence. This realization nudges us toward the next mystery, one that doesn't just push the limits of knowledge, but asks whether there are limits to what we can ever know. Imagine you're floating in the blackness of space, utterly motionless, surrounded by perfect emptiness. Not a single atom drifts by, no starlight warms your skin. According to quantum physics, this void should feel icy cold, a perfect zero on the thermometer. But now picture your ship suddenly lurches forward, engines roaring as you accelerate through the nothingness. In that moment, something impossible happens. Your thermometer spikes. The vacuum around you now glows with heat, a bath of warm particles swirling where seconds ago there was only emptiness. This isn't a malfunction, it's the Unruh effect, one of quantum theory's most mind-bending predictions, where motion alone conjures reality from the void. The effect is named after physicist Bill Unruh, who in 1976 realized that an accelerating observer would perceive particles in what an inertial observer sees as empty space. Think of it like this: two people sit in a pitch-black room, one stationary, the other spinning in a chair. The stationary person experiences pure darkness, but the spinning one begins to see faint, ghostly lights. Not because the room changed, but because their motion altered their perception of it. In quantum terms, the accelerating observer interacts with the vacuum's quantum fluctuations in a way that manifests as real, detectable particles, specifically, a thermal bath of radiation with a temperature proportional to their acceleration. Here's where it gets even stranger. These Unruh particles aren't just mathematical tricks, they carry real energy and can theoretically be measured. For a human astronaut, the acceleration needed to produce noticeable Unruh radiation would be so extreme it'd reduce them to plasma. But for electrons in particle accelerators or hypothetical future light speed probes, the effect could become very real. Some theories even suggest that the seething quantum foam at a black hole's event horizon might generate Unruh-like radiation, blurring the line between Hawking radiation and this acceleration-induced phantom heat. The implications shake the foundations of reality itself. If particles can appear or disappear based purely on an observer's motion, then what we call empty space isn't an absolute backdrop but a dynamic stage that shifts with perspective. It's as if the universe maintains infinite parallel realities, one where a region of space is empty, another where that same space teems with particles, and which version you experience depends entirely on how you're moving through it. This isn't just about measurements being tricky. It suggests existence itself is fundamentally relational, a cosmic dance where reality crystallizes from potentiality through interaction. Critics argue the Unruh effect remains untested. The temperatures involved are so faint that current technology can't detect them. yet ingenious experiments are inching closer. Quantum optics setups using ultra-accelerated electrons might soon catch whispers of this phantom heat. Others propose looking for Unruh-like signatures in the thermal noise of superconducting circuits, or even in the way rapidly vibrating atoms scatter light. If confirmed, it would be smoking gun proof that the vacuum isn't passive but responsive, a mirror that reflects back whatever motion we impose upon it. But the deepest mystery isn't technical, it's philosophical. The Unruh effect blurs the line between discovery and creation. When an accelerating observer detects particles, are they uncovering hidden layers of reality, or literally bringing that reality into being through their own motion? It's a question that echoes through quantum mechanics, from the observer effect to entanglement, whispering that the universe might not have a single, objective blueprint but infinite potential blueprints, each valid from its own frame of reference. This revelation doesn't just deepen our cosmic mysteries, it transforms them. If reality is this fluid, this observer-dependent, then the next frontier might not be outer space but the very nature of perception itself. What other hidden layers might emerge if we could only learn to move through the void in the right way? The answer could rewrite not just physics, but our understanding of what it means to exist. Picture this: you're floating in the void of deep space, utterly alone. No stars, no planets, just infinite darkness. Then, without warning, a fully formed brain pops into existence, complete with memories, thoughts, even the vivid sensation of reading these words right now. It lasts for a fleeting moment before dissolving back into chaos. That's the Boltzmann brain paradox, a cosmic thought experiment so unsettling it makes the simulation hypothesis seem tame. Named after physicist Ludwig Boltzmann, this idea doesn't just question reality, it turns it inside out, suggesting that self-aware beings like you and me might be nothing more than random blips in an otherwise lifeless universe. Here's how it works. The second law of thermodynamics says entropy disorder always increases over time. But Boltzmann realized that in an infinite universe, random fluctuations could occasionally create pockets of order, like waves forming brief patterns in a turbulent sea. Given enough time, even the most improbable events become inevitable. So statistically, it's far more likely for a single, fully formed brain to spontaneously assemble from chaos than for an entire ordered universe like ours to exist. After all, one brain requires vastly less coordination than galaxies, planets, and billions of conscious beings. The implications are dizzying. If Boltzmann brains are possible, how do you know you're not one? Your memories of childhood, your sense of self, even your certainty that the world existed before this moment, all could be illusions crafted by a random fluctuation. The universe wouldn't need stars or planets. It could be an endless void where conscious moments flicker in and out like fireflies in the dark. Even more bizarre, if these brains outnumber real observers like us, then statistically, you're probably one of them. But wait, it gets stranger. Some versions of the paradox suggest Boltzmann brains wouldn't just appear in space. They could emerge in time as thermal fluctuations in a universe approaching heat death. Picture the far future, trillions of years from now, when all stars have burned out and black holes evaporated. In that cold, featureless void, random quantum fluctuations might still spawn brief bursts of consciousness, each believing incorrectly that they inhabit a rich, structured cosmos. Your entire life, from first breath to this very second, could be one such fluctuation, a hallucination spun from chaos. Physicists recoil at this idea, not because it's disturbing, but because it's too probable. If the universe is eternal and infinite, Boltzmann brains should dominate all conscious experience. Yet here we are, seemingly embedded in a stable, ordered reality spanning billions of years. This contradiction is called the Boltzmann brain problem, and it's forced scientists to reconsider everything from cosmic inflation to the nature of time itself. Some theories, like the cyclical universe or holographic principle, try to sidestep the paradox by making ordered states like ours inevitable. Others propose that the universe isn't infinite after all, that it has boundaries or will end before Boltzmann brains can outnumber us. The real sting lies deeper. If consciousness can emerge from randomness, what does that say about free will or meaning? Are our grandest achievements, our deepest loves, just thermodynamic hiccups? Or is the paradox itself a clue, a sign that our understanding of time, entropy, or even observation is fundamentally flawed? Perhaps the universe isn't a passive arena where particles collide, but something more dynamic, with laws that inherently favor complexity over chaos. For now, the Boltzmann brain remains a ghost in the equations, a reminder that reality's foundations might be shakier than we thought. But it also offers a perverse comfort. If we're not fleeting fluctuations, then the universe must be far stranger and far more intentional than we've dared to dream. And that mystery pulls us toward an even deeper question. What if the cosmos isn't just allowing consciousness, but requires it? Every particle in the universe has a shadowy twin antimatter, identical in mass but opposite in charge. When matter and antimatter meet, they annihilate in a flash of pure energy, leaving nothing behind. By all rights, the Big Bang should have created equal amounts of both, canceling everything out in a cosmic fireball. Yet here we are, surrounded by galaxies, planets, and coffee mugs made of matter. The fact that anything exists at all hinges on a tiny, mysterious bias in the laws of physics called CP violation. A 1 in a billion fluke that tilted the scales in matter's favor. This isn't just a footnote in particle physics. It's the reason the universe didn't vanish before it began. The story starts in the 1960s, when physicists James Cronin and Val Fitch observed something bizarre in the behavior of subatomic particles called kaons. These particles occasionally decayed in ways that violated what was thought to be a sacred symmetry of nature, charge parity CP symmetry. Imagine flipping a coin and expecting equal odds of heads or tails, only to discover it lands heads 51 times out of 100. That fractional imbalance, magnified across the universe's first moments, could explain why a shred of matter survived annihilation. Later experiments with heavier particles like B mesons confirmed CP violation wasn't just a kaon quirk, it was woven into the fabric of reality. But here's the puzzle. The amount of CP violation we've measured in labs is far too small to account for the overwhelming dominance of matter today. It's like finding a single crooked brick in a demolished building and trying to reconstruct the entire blueprint. Some theories suggest undiscovered particles like hypothetical neutrinos with right-handed spins could have tipped the scales further. Others propose that the true asymmetry lies in the neutrino's very nature. If these ghostly particles are their own antiparticles, a process called leptogenesis could have seeded the universe's matter bias moments after the Big Bang. Picture a cosmic seesaw where neutrinos decayed slightly more often into matter than antimatter, cascading into the imbalance we see today. The stakes couldn't be higher. If CP violation were weaker, galaxies wouldn't exist. If it were stronger, the universe might have collapsed into black holes before life could emerge. This fine-tuning has led some to wonder, is our cosmos the product of random chance in a multiverse, or does its blueprint inherently favor existence? Experiments like the Deep Underground Neutrino Experiment DUNE are hunting for answers by firing particle beams through 800 miles of Earth to study neutrino oscillations with unprecedented precision. Meanwhile, the Large Hadron Collider scrutinizes quark-gluon plasma, recreating conditions from the universe's first microseconds to spot hidden asymmetries. Yet for all our progress, the mystery lingers. CP violation isn't just a particle physics curiosity, it's the universe's signature, scrawled in the margins of its own survival. And that signature leads us to an even deeper question. If the cosmos is built on such delicate imbalances, what else might be hiding in the fine print? Which brings us to the force that sculpts the cosmos yet defies explanation: gravity. Unlike the other fundamental forces, gravity refuses to play by quantum rules. It warps spacetime on galactic scales but vanishes into background noise at the atomic level. For decades, physicists have chased a theory of quantum gravity, a framework to unify Einstein's curvature with the frenetic dance of particles. Some propose gravity isn't a force at all but an emergent property of entropy, like cosmic thermodynamics. Others suggest it leaks into our universe from hidden dimensions, its weakness a clue to realms beyond our perception. The search for gravity's true nature isn't academic, it's a journey to the heart of reality itself. Because if we can decode why matter outweighs antimatter and why gravity bends the rules, we might finally read the universe's blueprint without smudges or missing pages. And that's a story still being written. Gravity is the universe's great architect, bending starlight, sculpting galaxies, pinning us to the Earth. Yet for all its cosmic dominance, it remains physics' greatest rebel, refusing to play by the same rules as the other fundamental forces. While electromagnetism and the nuclear forces bow to the strange laws of quantum mechanics, gravity stands apart, described perfectly by Einstein's general relativity, but vanishing into irrelevance at the subatomic scale. This isn't just a gap in our knowledge, it's a rift in reality's blueprint, one that demands a theory of quantum gravity to stitch the cosmos back together. Enter the contenders. Loop quantum gravity imagines spacetime not as a smooth continuum, but as a fabric woven from tiny, indivisible threads. Think of a t-shirt viewed under a microscope, its fibers revealing a granular structure invisible to the naked eye. In this framework, space itself is quantized, with these loops interacting to create the gravity we experience. It's a radical reimagining where even the vacuum has a texture, a pixelated foundation that could eliminate singularities like those inside black holes. Yet for all its elegance, loop quantum gravity struggles to explain how smooth spacetime emerges from this chaotic weave, leaving critics to wonder if it's missing a crucial stitch. Then there's string theory, the flamboyant showman of theoretical physics. It proposes that particles aren't zero-dimensional dots but vibrating strings, their harmonies dictating mass, charge, and even the fabric of spacetime. To make the math work, strings dance through 10 or 11 dimensions, most curled into spaces smaller than an atom. Gravity, in this view, emerges from the interplay of these strings, with the graviton, the hypothetical quantum of gravity, being just one note in a symphony of vibrations. But string theory's beauty comes at a cost. It predicts a near-infinite number of possible universes, making it notoriously difficult to test. Are we chasing a theory of everything or a mathematical mirage? And then there are the outsiders, ideas like causal dynamical triangulations, which treat spacetime as a mosaic of geometric blocks that evolve step by step, or asymptotic safety, where gravity becomes predictable at ultra-high energies without requiring new particles. Some theorists even suggest gravity isn't a fundamental force at all but an emergent phenomenon, like temperature arising from the motion of atoms. Imagine a crowd at a concert. Individually, each person moves chaotically, but collectively, they create waves that ripple through the stadium. Could gravity be the crowd wave of some deeper quantum interaction we've yet to uncover? The hunt for quantum gravity isn't just academic, it's a race to decode the universe's most urgent whispers. Black holes, where gravity and quantum effects collide, are cosmic crime scenes begging for clues. When Stephen Hawking showed black holes emit radiation and slowly evaporate, he exposed a paradox. Information swallowed by a black hole seems lost forever, violating quantum mechanics' core tenets. A working theory of quantum gravity could solve this, revealing whether information is scrambled, preserved, or funneled into parallel universes. Even the Big Bang, a singularity where all laws break down, demands quantum gravity to tell its true story. Yet the most tantalizing hints might lie closer to home. Experiments like the Laser Interferometer Gravitational Wave Observatory LIGO detect ripples in spacetime from colliding black holes, offering snapshots of gravity in its most extreme form. Meanwhile, tabletop experiments with supercooled atoms or entangled photons search for deviations from Newton's inverse square law at microscopic distances, potential fingerprints of extra dimensions or quantum spacetime foam. And if we're very lucky, the Large Hadron Collider might spot a graviton hiding in the debris of particle collisions, though its ghostly nature makes this a cosmic needle in a haystack search. What makes this mystery so exhilarating is its stakes. Unifying gravity with quantum mechanics wouldn't just fill a textbook gap, it would redefine reality. Imagine a world where spacetime has a grain like wood, where black holes are portals rather than prisons, where the Big Bang wasn't a beginning but a bounce from a previous universe. The answers are out there, written in the cosmic background radiation, the spin of distant pulsars, the quiet hum of empty space itself. And when we finally piece them together, we won't just solve a puzzle, we'll rewrite the universe's blueprint from the ground up. Which brings us to the final, most profound question of all. Is the cosmos a singular masterpiece, or just one thread in an infinite tapestry? The answer might lie where all these mysteries converge, at the edge of understanding, where physics meets philosophy, and the universe's greatest secrets wait. Einstein spent the last 30 years of his life chasing a dream, a single, elegant equation that could unite gravity's cosmic dance with the frenetic quantum world. He called it the theory of everything, a framework so complete it would describe the flutter of a butterfly's wings and the spin of galaxies with equal grace. Today, that quest remains physics' ultimate prize, a puzzle hiding in plain sight at the intersection of everything we've discovered and everything we still can't explain. Consider the forces shaping reality. Electromagnetism paints the sky with auroras and binds atoms into molecules. The strong nuclear force welds protons together in stellar furnaces, while the weak force orchestrates radioactive decay. And then there's gravity, the maverick, bending spacetime itself but vanishing into irrelevance inside atoms. These forces seem unrelated, like separate languages spoken by different corners of the cosmos. Yet physicists are convinced they're dialects of something deeper, fragments of a unified law we've yet to decipher. The clues are tantalizing, at energies high enough, like those in the universe's first trillionth of a second. These forces may have been one. Picture a prism splitting sunlight into colors. The theory of everything would be the pure, white light before the fracture. Grand unified theories, GUT, have already merged electromagnetism with the nuclear forces, suggesting they're facets of a single interaction. But gravity resists. While quantum particles exchange force-carrying particles like photons or gluons, gravity warps the very stage they perform on. Reconciling these visions, particles as discrete actors versus spacetime as a dynamic backdrop, requires a revolution. String theory emerged as a leading contender, weaving all particles and forces from vibrating strands of energy. In this symphony of strings, a graviton's hum would be no different from an electron's, just a higher note on the scale. But the cost, a universe with 10 or 11 dimensions, most curled into knots too tiny to detect. Then there's loop quantum gravity, which pixelates spacetime itself, or causal set theory, where reality is built from discrete, interconnected events. Each approach dazzles mathematically but stumbles when confronted with real-world tests. The stakes are cosmic. A true theory of everything wouldn't just fill textbooks, it would rewrite them. Imagine calculating what happened before the Big Bang, or predicting new states of matter lurking in neutron stars. It might reveal hidden dimensions brushing against our own, or explain why the universe's constants are so exquisitely tuned for life. Some even speculate that consciousness itself could emerge from this deeper layer, like droplets condensing from humid air. Yet the dream's elusiveness whispers a humbling truth: the universe's blueprint might not be simple. What if everything can't be captured in one equation but requires a mosaic of perspectives, each valid in its own realm, like maps of a city seen from different altitudes? Or what if the answer has been staring at us all along, encoded in the symmetries of particles or the holographic hum of black holes? As we stand at this frontier, the quest itself becomes the revelation. Every dead end exposes hidden assumptions. Every near breakthrough stretches the limits of imagination. Whether the theory of everything is a single Rosetta Stone or a library of interconnected truths, the search reminds us that the universe is richer, stranger, and more connected than we've dared to dream. And that, perhaps, is the most beautiful mystery of all. Consciousness might be the most intimate mystery we'll ever confront, not just because it defines our experience of reality, but because it forces us to ask a question so profound it echoes through the cosmos. Is the universe itself aware? This isn't just poetic musing. Cutting-edge theories in physics and philosophy are flirting with the radical idea that consciousness isn't an accidental byproduct of brain chemistry, but a fundamental feature of reality, woven into the fabric of spacetime like gravity or electromagnetism. Imagine if the cosmos weren't just a cold, indifferent machine, but a vast, self-reflective network where observation and existence are inextricably linked. The roots of this idea stretch back to quantum mechanics' strangest quirk, the observer effect. In the famous double-slit experiment, particles behave as waves when unobserved, but collapse into definite positions the moment they're measured. It's as if reality remains fluid until consciousness pins it down. Nobel laureate Eugene Wigner took this further, proposing that a conscious observer is necessary to finalize quantum events. While most physicists today attribute collapse to environmental interactions, the deeper question lingers: why does the universe seem to care whether we're looking? Some theories push this even further. Integrated information theory, for instance, suggests consciousness arises from the complexity of information processing not just in brains, but in any system with the right architecture. A star, a black hole, even the universe itself might possess some dim, alien form of awareness. Then there's panpsychism, the ancient idea reborn in modern physics, which posits that consciousness is a universal property like mass or charge. In this view, electrons might have infinitesimal slivers of experience, and complex systems like brains simply amplify and organize these fragments into self-awareness. But the most staggering proposal comes from the participatory universe hypothesis, championed by physicist John Archibald Wheeler. He envisioned a cosmos where observation doesn't just record reality, it creates it, retroactively shaping events back to the Big Bang. Picture a cosmic game of 20 questions where the universe only settles on definite answers when questioned. If true, this would mean the universe evolved conscious observers not by chance, but because their gaze is what brings it into focus. It's as if the cosmos dreamed us up to witness itself. Critics dismiss these ideas as metaphysics masquerading as science, and they're not wrong. Proving consciousness is fundamental is like trying to bite your own teeth. Yet clues might lie in the universe's uncanny fine-tuning. The constants of nature are balanced with razor-sharp precision to allow for stars, planets, and life. Is this just luck, or does consciousness play a role in calibrating reality? Some interpretations of quantum mechanics even suggest that without observers, the universe would remain a fog of probabilities, never collapsing into concrete history. The implications are dizzying. If consciousness is built into reality's blueprint, then the line between observer and observed blurs beyond recognition. Your thoughts aren't just electrical storms inside your skull. They're threads in a cosmic tapestry, participating in the universe's unfolding. Black holes might encode information in ways that resemble memory. Dark energy's acceleration could reflect a kind of cosmic growth. Even time's arrow might be tied to the flow of experience rather than mere entropy. This isn't just philosophy, it's a frontier. Experiments are probing whether conscious intention can influence quantum systems, however subtly. Others study brain dynamics for signatures of quantum coherence, hunting for links between mind and quantum reality. And if we ever crack the hard problem of consciousness, why subjective experience exists at all, we might find it's not a problem to solve, but a clue to the universe's true nature. So the next time you gaze at the stars, consider this: you're not just a speck in the void, you're the universe's way of knowing itself, a spark of awareness in an ocean of potential. And that might be the greatest mystery of all, not just how the cosmos works, but why it feels like anything at all. From dark matter's invisible scaffolding to the holographic whispers of spacetime, these 32 cosmic riddles don't just define the edges of our knowledge, they tear them wide open. Every mystery we've explored is less like a locked door and more like a fractal. The closer we look, the more intricate it becomes. Take dark matter, for instance. We've mapped its gravitational fingerprints across galaxies, built detectors deep underground to catch its faintest murmurs, and yet it slips through our grasp like smoke. It's not just that we don't have the answers, it's that every answer births new questions, each more baffling than the last, and that's the exhilarating truth of cosmology. The universe isn't a puzzle waiting to be solved, it's a living conversation, one where we're just learning to speak the language. Consider the holographic principle, the mind-bending idea that reality might be a projection from some distant two-dimensional surface. It sounds like science fiction, yet the math sings with elegance, suggesting that every star, every atom, even your awareness of these words, could be pixels in a cosmic display we're only beginning to decode. The beauty isn't in cracking the code, but in realizing how much code is left to read. This isn't failure, it's liberation. The moment we think we've pinned down the universe's rules, whether gravity's quantum secrets or the true nature of time, the cosmos tosses us a curveball. Black holes evaporate, particles entangle across galaxies, the vacuum of space crackles with phantom energy. These aren't flaws in our understanding, they're proof that reality is richer than our boldest theories. The night sky isn't a static painting. It's a living, breathing enigma, one that rewards curiosity with ever deeper wonder. So as you step outside tonight and look up, remember, you're not just seeing points of light. You're witnessing the universe's grandest mysteries in real time. Every flicker of a star, every dark patch between them, holds questions we're still learning how to ask. And that's the greatest gift science gives us: not answers, but an endless frontier of awe. The adventure isn't in reaching the destination, it's in knowing the journey never ends. Now it's your turn. Which of these cosmic secrets keeps you up at night? Is it the haunting silence of the Fermi Paradox, or the way quantum particles seem to dance to an unseen tune? Drop your thoughts below. We're all stargazers here, piecing together the universe one wonder at a time. And if you're hungry for more deep dives into the unknown, hit that subscribe button. The cosmos has plenty more to reveal, and we're just getting started. After all, the universe doesn't give up its secrets easily, but that's what makes the